Welcome to lesson 2.1, using inductive reasoning to make conjectures. The learning targets for this lesson are that you will be able to use inductive reasoning to identify patterns and make conjectures, and that you should be able to find counterexamples to disprove false conjectures. So the first thing is identifying patterns. So when we're looking at these numbers, we're looking to see if we can find a pattern. I'd like you to pause the video for a moment and see if you can try letters A through H and if you can get the correct answers on your own. Here are the correct answers for A through H. I will go through a brief description of them in case you got them wrong. If you did get them all correct, feel free to fast forward till you see a pink star next to the word reasoning. All right, find the next term in each sequence or in each pattern. So right now, I look and see, well, how are they getting the next number? They're getting really big, so they're not adding something. They're actually multiplying by 3. 4 by 3 is 12. 12 by 3 is 36. 36 times 3, 108 times 3. So the rule that they're following is they're multiplying by 3. Letter B is a little tricky to figure out because you don't see a pattern, right? They added 0, they added 1, they added 2, they added 2 again, they added 3, they added 5. That doesn't make sense. It's actually called the Fibonacci sequence. And so what they're doing is adding the previous two terms. This one plus this one gives us this one. 1 plus 2 gives us 3. 3 plus 5 gives us 8. 8 plus 13, or sorry, 5 plus 8 gives us 13. 5 plus 8 gives us 13, and 8 plus 13 gives us 21. So you have to add the previous two terms. Letter C, you can see the pattern. They keep adding another odd number, and when they do this, we're getting perfect squares every time. So we first got 1 squared, then 2 squared, then 3 squared. The next one will be 4 squared. Next we would see 1, 3, 5, 7, 9, and that would be equivalent to 5 squared or 25. Pattern for D, they keep multiplying. They keep adding 1 to the number, so it started out as 11 by 11. Now it's 111, so they're adding 100. They just keep going up by a tens place or by a place value. And so when they do that, there is a pattern that emerges. So we, by having 4, the number in the middle, whoops, the number in the middle is 4. I had to put the 3 there. E is skipping every other month, starting in January. Number 7, that's just multiples of 7, or they keep adding 7 to get the next term. So add 7 to the previous term. Letter G, geometrically, they are rotating it on 90 degrees clockwise each time. And letter H, it's rotating between vertical lines and horizontal lines, vertical lines and horizontal lines. And every time they rotate it, they add another line in a circle to it. Inductive reasoning. Got to put our star down. Inductive reasoning is where we are predicting or drawing conclusions or making predictions based on observations, usually of patterns. A pattern is identified. And that pattern is true for several things, and so we assume that it's going to continue that pattern. So inductive reasoning, drawing conclusions, making predictions based on observations or patterns that we've identified. For example, letter D is probably something you've never seen before, But if you observe the pattern, you could figure this out. You could also verify it with your calculator. It remained true, which was pretty cool. Same thing with letter C. You may not have known that the sum of the odd numbers, if you take however many odd numbers you're adding up, that would be the number squared. You might not have known that, but you can see that in the pattern, or you can figure out the pattern to get the next row. The same thing is true with other things, not just in mathematics. When you are making a prediction or drawing a conclusion based on what you have observed, not what you were told as a fact or what people have generally accepted as a fact, but you're accepting that this pattern will keep going or making predictions based on it, you are basing your conclusion on inductive reasoning because you're basing it on what you've observed. A conjecture is an educated guess, often and usually based in inductive reasoning. So we're going to complete the sum, or we're going to complete these conjectures. And some of them you will know immediately because you've just memorized them as facts. You explored them in middle school. By the way, all the explorations we do, where you're drawing conclusions based on some things that you've done and you're seeing patterns and figuring them out, that's all inductive reasoning. Whereas deductive reasoning is where we base things off of things that we were told as true or told as fact. But we'll get into deductive later. So example 2, complete the conjecture. Now, when we make a conjecture, it needs to be based on inductive reasoning or based on patterns that we've seen. So we need to observe a few being at least 3 examples or cases. We'll call them cases, and you can make your own up to draw our conclusion or to make our educated guess, our conjecture. So the sum of 2 positive numbers, well, you know this because you kind of memorized it in middle school, it's going to be positive. But if I were trying to convince somebody who hasn't learned that yet and they're just getting into negative numbers and they don't know that the sum of 2 positive is always positive, I would show them and see if they could figure out a pattern. And I'd say, look, here we've got all these cases. Look, I have a positive number and another positive number, and it got me a positive number every time I added it. Now the trick would be, does this always hold true? This one is a rule we know always holds true. There are no positive numbers that you could add together that would give you a negative. So this one is always true. We know it as a fact. But these are some observations that could be made to draw that conclusion. The number of lines formed by 4 points, no 3 of which are collinear. So that's going to be a quadrilateral, right? Because there are only 2 are collinear. It takes 2 points to make a line. So we're going to explore this a little bit. We've got 4, 5, 6. I don't think I can connect any other ones. So we're going to have 6 is the number of lines we can form. You might have known that off the top of your head, but most likely not. Even if you did, you probably were visualizing it. The product of 2 odd numbers. This one you may not know. Take a moment to read these problems and see if you can make a guess on what will happen, but provide some evidence that leads you to your conclusion like we did up here. In this case, the product, that's multiplication of 2 odd numbers. So for every example that you're exploring, I should see 2 odd numbers and that you've multiplied them. And then you're going to write your conclusion. And then do the same thing through letter D. Take a moment to pause the video, see if you can figure those out. These are the answers that you should have gotten for letters C, D, E, and I'm not sure what happened to F, but G. So the product of 2 odd numbers is odd. We can convince ourselves or someone who doesn't believe that by showing them. 3 times 5 is 15. 5 times 7 is 35. 9 times 11 is 99. You make up your own numbers. You shouldn't have the same ones I have. But you can see an odd times an odd give us an odd, and it's working every time. So that's our conclusion. Letter D, everywhere she goes that has a cat, she's having a reaction. and itchy, watery eyes. So our conclusion, and it might not be true, she'd have to get formally tested to know for certain, maybe there was something else there other than a cat that led her to have this reaction. But as far as we know, based on the information we know and what we are observing, or the pattern that we're observing as we read this information, is that she's probably allergic to cats. Product of two even numbers, so maybe you did 2 and 4, or 8 and 6, or 50 and 6. Every time it turns out to be even. And the smelly teacher one, the conclusion is, since they are all smelly, that last one's smelly too. All right, so those are our conclusions for me. That's how we make conjectures. We do need to observe a pattern when we're making a conjecture. You do this all the time in investigations. You did it in middle school. We'll be doing them in some of our explorations in geometry. To show a conjecture is true, you must prove it for all cases. It has to be proven that it is always true. It can't be true except for this exception or that exception, unless we're defining things that way. But for what we're doing, at least in the mathematics and the geometry part of it, you must have, and Euclid had to go through this too, he had to find a way to prove that it was always true. That's why we have some things that are called postulates and some things that are called theorems. The postulates were those things that remember the first 5 postulates, 2 points make a line? He couldn't find a way to prove it other than to show people with examples. And so since he could only show them for specific lines that he drew or specific points that he plotted, it was a pattern that he observed was always true. He could never find anything that didn't make it true. So that's why he called it a postulate. If it was something he could prove, it was called a theorem because he could prove that it would always work no matter where the points were, no matter what the lines were, no matter what the shapes were, it would always work. So postulates are things that we can prove, and theorems are things that we assume to be true without proof. Assumed true without proof. Because we really can't prove them. There's no way to prove them. But we know for a fact everyone agrees in common that those things are true. We'll get to that in a later lesson here also. So we're not ready to prove they're true. We could convince people using inductive reasoning, but we're not ready to prove stuff is true just yet till we get to our deductive lesson. But if we want to show that a conjecture is false, we only need one thing. We need to find a counterexample. A counterexample is a case, and it could be a number, it could be a picture, it could be a number of things. A number, a picture, a number, a drawing. I'm trying to think there's one more thing it could be. But it's a case that meets the conditions, or the first part, that meets the conditions, which we'll get into even more tomorrow, being the first part of the sentence, but shows a different result. But shows a different result. A case that meets the conditions, the first part of the sentence, but shows a different result. For example, I could say, the sky is always blue. And maybe I have a way to prove it, maybe I don't. But if you said, well, Mr. Ritter, at sunset, I watched the sunset over Lake Michigan earlier this summer, and the sky was orange. Okay, well, there's a counterexample. So my statement that the sky is blue, or the sky is always blue, is false. It's not always blue. There are counterexamples or cases. You don't need to find multiple. You only need one. So you need to find a case. You don't have to find 3 cases or 4 cases that prove it's false. Any one case that proves that meets the conditions. Hey, we were talking about the sky. We're still talking about the sky, but now it's a different color. So you were wrong, Mr. Ritter. It's not blue. Okay? So we'll get more into that. It's a little more involved than that, but in general, that's what a counterexample is. Show that each counterexample or each conjecture is false by finding a counterexample. 2 complementary angles are not congruent. So the condition is the first part. What I'm going to find for my counterexample has to be complementary angles. So my angles, whatever I pick, they better add up to 90. If they don't, then it's not a counterexample. But they're saying that they're not congruent. If I'm going to prove this false, I need to find something that would make that would actually be congruent. Well, most of you already know what it is, right? 45-degree angles, 90 split in half, 45 and 45. We could have two 45-degree angles. By the way, it doesn't have to be that. It could be this picture. Here's a 45-degree angle. Here's a 45-degree angle. They don't even have to be connected. Those two angles are going to add up to 90 degrees, which means that they are congruent. They are congruent. So here's I can have my counterexample be this picture that's showing that they're 45 and they are congruent. That they're going to be complementary because they're going to add to 90. So I just need one. I don't need to find other things. I found one case. For every integer, remember integers are our counting numbers, both positive, negative, and 0. N cubed is positive. So we probably should take a side note and talk about the number sets just to review from middle school. But these are positives, negatives, and zero counting numbers. Negatives, positives, and 0. So if I weren't sure if this were true, I would actually test all three. I'd test some positive numbers, I'd test 0, I'd test some negative numbers. But they want us to prove that it's false. So I need to pick an integer. It can't be a decimal or a fraction. It has to be a whole number or the opposite or 0. And I have to cube it. And they say the result is going to be positive. Well, if I cube -1, -1 times -1 is +1, times -1 is -1. So I just found the counterexample. The counterexample would be n equals -1, because that meets the conditions that, yes, it's an integer, but when I cube it, I don't get a positive number, I get a negative number. For any 3 points in a plane, there are 3 different lines that contain 2 of the points. For any 3 points in a plane, there are 2 lines that contain, or there are 3 different lines that contain 2 of the points. Well, I drew it that way, but I don't have to make them non-collinear. Right now it's true. So let me make them collinear. And they're all in a plane, but I can only make one line. So it says 3 different lines that contain 2 of the points. I only have one line. You can draw as many lines over that as you want. It's going to be the same line. So this is false, and there's my counterexample. Not those 3 points, but those 3. For the last one, for every number, any number, since they're not restricting it to my integers, which are not decimals, but negative, positive, and 0 counting numbers, I can have fractions, I can have decimals, I can have something crazy like pi. I can have fractions, I can have decimals, I can have negative numbers, positive numbers, 0. So if I weren't sure if this statement were true, I would test all of those. And if they all worked, then I'd assume, okay, maybe it's true. But I know that it's false because they're telling me to find a counterexample. So we have to pick a number that looks like one of these, that when we square it is not greater than the number we started with. So some of you are like, oh, pick a negative. Well, if you square negative, you get 9. And 9 is greater than or equal to -3. And that would be true even if I put a positive in there. You get the same thing, right? It would still give the same thing. So those are true, so that's not a counterexample. So now maybe 0. Well, that's greater than or equal to. 0 would equal 0, so 0 squared is greater than or equal to 0. That's still true. I have not tried fractions. Let's try 1/2. 1/2 squared, so I'm comparing the square of 1/2 to 1/2. 1/2 squared, 1 times 1 is 1, 2 times 2 is 4. 1/4. 1/4 is not greater than 1/2. So here's my counterexample, x equals 1/2. So I would say false, x equals 1/2. This statement is false. X equals 1/2 is my counterexample that proves that it is false. Steps to inductive reasoning. We've kind of already talked about this. You need to look at least 3 examples or 3 cases to try to figure out, do you think it's true? In the case of this problem right here, if I wasn't sure, if they didn't tell me that this was false, that I was finding a counterexample, I might not know. I need to test, since it's any value, any number, a positive number, a negative number, 0, a fraction, irrational numbers like pi or the square root of 2. If they tell me it's an integer, then I need to test the sets of integers. Do the negatives all work? Do the zeros work? Or does 0 work? Do all the positive numbers work? Test some and see if it works for all of them, then it's probably true. It might not be, but hopefully you've exhausted all the things that you could check. Determine if a conjecture is true. Once we've examined that, we can decide if it's true. If it's not, then in our exploration of it, we should find out one that makes it false. So then we would say false and give the counterexample. The quotient of two negative numbers is always positive. Okay, so negative numbers. Let's do -2 times -3. That's +6. Okay, I'm pretty sure this is true. Most of you already knew this, right? Oh, quotient, supposed to be dividing. -6 divided by -3 is 2. -8 divided by -10 is 4/5. -100 divided by -25 is +4. They're always positive, so I believe this is true. And while this is not a proof that I've given here, I am showing people, here was my logic, here are my 3 cases that I explored to make sense of the problem and see if I thought it was true. Even if I know for a fact that it is, I'm still going to show some cases to convince other people. The next one, every prime number is odd. Prime numbers are divisible only by 1 and themselves. So 1 is prime. Some of you jumped to 3 and 5 and 7 and 13. The other numbers between these, all of them except for 1 are not prime, but one of them is, and that's 2. 2 is only divisible by 1 in itself. So 2 is not prime, or 2 is prime, so I would say false, 2, because 2 is prime, but 2 is not odd, 2 is even. So that's what our counterexample has to do. It has to meet the conditions. The conditions was it had to be a prime number, but I had to show that it wasn't odd, it was even. 2 supplementary angles are not congruent. I'll let you try that one. We had an example of that above. Try these 4. Explore some numbers, see if you can figure it out. We're going to go over the answers in just when you come back to the video. All right, so hopefully you got these. 2 supplementary angles are not congruent is false. Supplementary are 2 angles that add up to 180. But that doesn't mean that they can't be congruent. In fact, if you have 2 right angles, you can say here's angle 1 and here's angle 2. I got 2 right angles, they're both 90 degrees. They're supplementary, but they are congruent. That's what makes it false, is that they are congruent. The square of an odd number is odd. 3 squared is 9, 5 squared is 25, 7 squared is 49. You can try other combinations, but this tends to be true for every case you could come up with. That is true. And angles formed by a linear pair are congruent. Angles formed by a linear, no, just because they're a linear pair doesn't mean they have to be congruent. So here's my counterexample, angles 1 and angle 2. I say false. Here's my linear pair. I'm at the first part of the sentence, but they're not congruent. This is clearly smaller than this. In fact, I'll label this one to be 30 degrees and this one to be 150 degrees. Still a linear pair because they're adding to 180, and they're connected by a common ray, but they're not congruent. The distance of 2 negative integers, difference of 2 negative integers is negative. So -3 minus -2. That's going to be -1. Sure, so far it's good. Let's try -2 minus -10. Uh-oh, because it becomes the positive, that's going to be 8. So I can instantly say this is false. I don't need to test anymore because I found a counterexample. There's 2 negative numbers, -10 and -2, and when I subtracted them, took their difference, I actually got a positive answer. This concludes the notes for today. Hopefully you are able to say, yes, I get what inductive reasoning is. It's based on observations, drawing conclusions, making conjectures based on observations. And counterexamples are when we just need one case that makes the statement untrue, makes the first part of the statement true, and the last part a different conclusion. Have a great day.